Hello guys, here we are going to solve another problem related to insulation design. So in the problem statement, we are given that we have a feed through insulator, which means we have a conductor passing through multiple layers of insulations. So this is a conductor, then we have multiple layers of insulation as labeled um, 2, 3 and 4, and the diameters of each of them are shown here. Diameter of the cable is D1, diameter of the cable including first layer of insulation is D2, then D3 and then D4 and so on. And also we are given the lengths of different layers as well as L4, L3 and L2. In the question, we are required to find L2 and L3. We are required to find these, and we are given the L4 is given, and also we are given all of these D1, D2, D3 and D4. And on top of this we are given a condition that we have inserted thin metal sheets between multiple layers, between the layers, which means we have inserted one metal sheet here, we have inserted another metal sheet here, so here, okay. So the purpose of inserting these metal sheets was to create equal maximum electric field strength at this point and at this point. Okay? And remember not to forget that these are cylindrical geometries. Actually, these are cylindrical shapes. We are looking at the side view. So this is in fact a cylindrical shape like this. And this is also a cylindrical shape like this. And this is also a cylindrical shape. Okay, so this looks like this, like a like concentric cylinders, as you can see. Okay, so now we know that the electric field distribution in concentric cylindrical assembly is like this. We have zero electric field inside the conductor, then we have maximum electric field at the surface of the conductor, then it decreases um, in an inverse relation to the radial distance when we go outward from the surface of the conductor. Then at another, when it reaches to another layer, when it reaches at the interface between the two insulations, like I have labeled here, then electric field will be maximum again, then it will decrease, then when it will arrive another interface, then electric field will be maximum, and so on. So electric field is maximum at all of these interfaces, at the surface of the conductor, at the um, interface between layer 2 and 3, and at the interface between layer 3 and 4. And we know that the electric field E is given by, in case of cylindrical geometry, Q over 2 pi epsilon L R. And when we talk about maximum electric field, E max, then it will be Q over 2 pi epsilon L and internal radius, okay, inner radius of the conductor. So now here we have maximum electric field. So here we have Ri, for example, radius of conductor, or we call this as d1 by 2, d1 by 2. So we will have maximum electric field at this point, which is the radius is d1 by 2. Then at this point, we will have d2 by 2. At this point, we will have d3 by 2. Okay, so these are the points where we will have maximum electric fields. And what about the lengths? What kind of, okay, we will take these radial distances as d1 by 2, d2 by 2, d3 by 2 for all these 3 points. What about the lengths? Now at the surface of the conductor, we have length L2, as you can see here, from here to here. So length of the insulator is L2. Then we have at the interface between the first and the second layer of insulation, we have length L3. Then we have length L4. So at this point, we will take L2. At this point, we will take L3. At this point, we will take L4 as lengths. Okay. So now our electric field, so Emax can be written as Emax can be written as Q over 2 pi epsilon L2 d1 by 2 at this point. Then at this point, electric field is also equal, so that is equal to Q over 2 pi epsilon L3 d2 by 2. Okay, and then at this point, electric field is also equal. Maximum electric field will be given by Q over 2 pi epsilon L4 d3 by 2. So these are our equations. Okay. Now if we equate the first two, these two, we can see, okay, the charges will also be equal because we will have the same equal amount of charge on each of the layers. So on each of the interface. So charges are equal, 2 pi epsilon is equal. And now when we will equate these two, 1, 2, and 3. So when we equate 1 and 2, equating 1 and 2, we will be left with only L2 d1 . Okay, if we equate 1 and 2, we will not get anything out of it because here we have L2 variable and here we have L3 also unknown. So we have L2 and L3 unknown. So instead of equating 1 and 2, we need to equate 1 and 3. So if we equate 1 and 3, then we will get we can determine one unknown. So L2 d1 will be equal to L4 d3. Okay, so now we have all the values. We have d1, d3, d4, and d2, and we also have L4. So the only thing unknown in this equation is L2. So if we put the values, and we can determine L2 will be equal to 336 millimeter. Okay. Similarly, by equating 2 and 3, term 2 and term 3, in equation A. Okay, so we will get L3 D2 equal to L4 D3. Again, here D2, D3 and L4 are unknown. Sorry, they are known. Only unknown is L3. So we can get the value of L3 as, after plugging the values, we will get the answer 198 millimeter. Okay. So we have determined the required parameters which were asked in the question. Design the lens L2 and L3 so that the maximum field strength in both the sheets is of the same magnitude. Now, what is this maximum field strength value? So, how much is the maximum field strength value? That's what we need to determine, and that's really easy. So, the total voltage applied here in this geometry, the total voltage applied will be distributed between the multiple layers. So we will have voltage, if we are applying total voltage U, that will be distributed between the first and the second layer, U12 plus U23 plus U34. Okay, so as we can see here, so it will be distributed between the three layers of insulation. So insulation 1, insulation 2 and insulation 3. So between the points 1 2, 2 3 and 3 4. And we also know the expression for the, or the relationship between the voltage and the electric field is U is equal to Q over 2 pi epsilon L and ln of Rho over Ri. That was our uh, expression. This can also be written in terms of electric field, that is E R ln of Rho over Ri. And we can also write in terms of breakdown voltage. So UB or Umax is equal to Emax, and maximum electric field occurs at the internal radius, and then natural log of Rho over Ri. So we are going to use the same relations for all of these insulation layers. So U12 can be written as Emax, and radius will be the d1 by 2, because that will be the radius of the conductor itself, and then ln of, either we can put r2 by r1 or we can put d2 by d1. So the ratio of the diameters is equal to the ratio of the radius always, plus Emax for the second term. Maximum electric field is equal at all these interfaces. So again, we will have Emax d2. Now we will have d2 by 2. Radius will be d2 by 2. And natural log of d3 over d2. And then we have, for u34, we will have Emax again d. Now we will have d3 by 2 and natural log of d4 by d3. Okay, so after putting all the values, after plugging all the values, and we are also given the voltage, which is 30 kilovolt. So after plugging all the values, the only unknown is Emax. We can take Emax common, on the right side and plugging the values. So Emax will be equal to 1.73 kilovolt per mm. Okay, so this concludes our solution. Thank you.